So this lecture, so we have a little bit different agenda for today. So a little bit different agenda. So today is the 9th of October. And we will have the lecture until the first lecture. There will be a lecture, and afterwards, since 5 o'clock until the 6 o'clock, Yegor will give you explanation about the project. And it will be based on his research, and he will share with you his own experience about his own research and give you some insights about what kind of project you can do for this course. Yegor will give you some like a workshop about project. Yeah, like this. So this is the material for today. So we will cover, I believe we will cover kinematics today, and tomorrow we'll cover dynamics. Since tomorrow we also have a lecture, right? Yes, great. So today we will cover spatial kinematics. But before we proceed, let us just remember what have we done so far. So we have covered modeling. So now we know that it's act of creating a model. We have done a model of mass spring damper. Then we covered integration, such that we can use this model to simulate, to understand the behavior and the performance of the system. Then we have modeled 2R robot. So we covered kinematics, forward kinematics, inverse kinematics, forward dynamics, and for like inverse dynamics. And we have done the model. Then we take a look at how this model can be used to do a passive model without control with a pendulum. But you can do the same for the 2R robot as well. And also we have done this linearization thing to do efficient control for the fully actuated system. And finally, we covered bone growth theory as a methodology to model different physical domains, and that the methodology that gives insight about the physical foundations of robotics. Okay. So right now we will cover spatial kinematics. So here, this is that we covered yesterday, and right now we will cover material of the chapter 4. So this is the task for us for today. So here you will find a lecture notes, but right now we will go through it such that we understand the concept. So also what I would like to show you, so you have also a link to the Yandex Disk, and you can find slides from the previous year. So you can also use it as a material. And I'm going to use both of them. but you will see the iPad screen. So the idea that must be covered, the first idea that must be covered is the idea between explicit and implicit coordinate representation. Explicit versus implicit coordinate representation. So the implicit, basically explicit, means that you have n parameters, basically n numbers, to describe an dimensional space. Dimensional space. And it's something that we covered yesterday. We had planar case that has 3 degrees of freedom in general in planar, and we had 3 equations for the coordinates x, for the y, and for the angle. And for example, if you consider a point mass, for example, or just a point on a plane, this is x and y, and here the position, you need 2 numbers to describe position, and the velocity will be a time derivative of it. So it's a rate how the coordinates changes. And the relationship between position and velocity will be like the same for the whole space. But if we'll take a look at not on the plane, but on a surface, for example, a sphere. So look, this is a sphere, like a 3D sphere, like a globe. In order to describe a position, on this sphere, how many coordinates do you need? 2, right. And it will be something which is called latitude, and longitude, longitude, right? But if we then will try to represent this surface as a plane, it's just like a globe and a map, right? And the map is distorted. And let's assume that this will be the latitude, and this will be the longitude. What will happen, for example, let us consider that you are here and you do one step, like 1 meter step, and and the next time you are here and also you do this 1 step. So in absolute values it is the same step, but in relative coordinates it will be different. So here the one step will be something like this, but right here that represent this position, this state, it will be something like this. And here it will be just something like this. And it's called singularity. And it happens since we have different topology. So the planar case is something which is called just R2, and for the sphere it's called S2. So we have different topologies, and the first chapter in the modern robotics book describe this concept. And in order to get rid of this stuff, we use not 2 points, not 2 coordinates, but 3, right? X, Y, and Z. So, and if you will use X, is it X? Let me be. This will be, for example, X, Y, and Z. Yeah. And you will get rid of this singularity. But what do? You actually use 3 numbers to describe a point in 2D surface, 2D space. So implicit coordinate representation means that you use m parameters to describe m-dimensional space. M. N. Yes. N. And M is greater than N. And this is why it's implicit. Okay? And for the implicit representation, time derivative of position will not be velocity. Kinda. It's not called the constraint, something else, and we will cover this. So basically, time derivative of this representation is kind of nonsense. It will not give you the velocity. You need to do something else. So let us consider the next situation. Let's assume that you have a physical, a little bit of notation. So if you have something like P, Pi, Q, so there is no superscripts. It means it will mean a physical point. It's not numbers, it's just a name. Okay? Superscript. For example, P, comma, Pi, comma, Q, but with J, this J is a superscript. You see? There is nothing else here, but here we have a letter, and this letter is called a superscript. It's like not in the power of J, but it's just extra letter that next to the letter. And this is the this will be a race of numbers that represent position of a physical point in a frame J. Arrays of numbers that represent the physical point expressed in a frame J, CJ. All right, so let's assume that you have a physical point P and you have two frames. This will be the first frame and we will title is as a frame 1. So C1. And a frame, the second frame that has the same origin, this will be the frame C2. So, and this will be x unit vector C2, Y2, Y1, X1. And you can see clearly that there is an angle between them. You can write the following. So the intuition. You can do a projection and you can write down something like this, that x1 equal to x2 plus, it's like a, this bar means that it's a vector, y1 plus y2. And now we can just project it on a x1, just any vector. So instead of x2, it will be it will be this part. So it will be x2 times cosine, right? So x2. So now it is like a value, and since it's unit vector, it will be equal to 1, right? x2 times cosine of theta plus y1 times cosine of p2, right? P over 2, and it will be 0. Plus y2 times cosine of basically this is the angle, so it's it could be minus, but I mean it's trigonometry. You can just it's a sum of this p over 2 plus theta. So I need some space here. So it's very convenient to use iPad for this stuff. Okay, so x1 will be x2 times cosine theta plus y2 minus sinus, so minus y2 sinus theta. So the same story with the y, but I will write for the answer. It will be x2 sinus theta plus y2 cosine theta. And it turns out that you can write it in a matrix form, and it will be x1 y1 cosine theta sine theta minus sine theta cosine of theta. x2 y2. Do you agree? And basically, what have we done? Spoiler. Yes. But I really want to show you the idea why it's true and what does it represent. So basically, P is just a point, physical point. It doesn't care what kind of numbers we use. It doesn't know anything about numbers. It's just something that human beings created. You see? And this is the representation, numerical representation of a physical point in the frame 1. In the frame C1. And this is for the frame C2. The same point, but just in different coordinates. And this is the relationship between them. It's something that maps one with another, and you can go from one to another. And it happens to be called a rotation matrix. That matrix describe how coordinates change. And what will be the determinant of it? 1. So it will be just like cosine times cosine, cosine in power of 2, sine times cosine in power of 2, with a minus, so 1. And the idea of determinant, determinant shows how this multiplication modify the vector, how it scale it. And since we just changed the interpretation, we didn't shrink it, we didn't scale it. And this is why it equals to 1. So now you see the physical meaning. So if the determinant is something different, so it's more than 1, it will be, yeah, it's like you have scaled it. It's less, you shrink it. And there is a very great YouTube channel which is called something like three browns, three blue, blue, one brown, and the guy have done amazing cartoons about math, and I was just mind-blowing when I was watching. It's just wow, nobody has told me the math how beautiful it is, and I spent like a night watching these videos, and really encourage you to take a look at this. It's just great. It's just not like a boring bullshit. It's just very interesting, and the voice is great, and the video and animation is just perfect. And he also has a video of this determinant. Okay, so x1, y1, we will say that it is p, but in the frame 1. So 1 is a superscript here. It's not in power of 1, it's a superscript. P2, it will be p expressed in the frame 2. And the notation will be P1, R1, 2, P2. And you can think like, we can do like this, and you will get P1. Just mnemonic rule to understand. This is Stefan notation. Notation. Lynch use a different one. Featherstone use the third one. Mark Spronk will use the fourth one, and etc. etc. This is Stefan called that. This is something which is called Einstein notation. Maybe he just wanted to make a point. It is the proper way to write stuff, you know. But it's always the pain in the ass, the notation that all of them have different notation. It's not like something that been fixed. Okay. Properly speaking, rotation matrix can be written in a different manner. So right here, and what else? What I would like to tell that if P1 equal to R1 to P2, then P2 will be R21 P1. It's like you can go from there to there, and the rotation matrix is a special one. It's actually called the special. It's called special orthogonal group. It's so rotation matrix is special. Not a spatial, but special. But also it's spatial. Okay, is special. And it's called special orthogonal group. And it's denoted as SO3. But that one, the particular one that we have written, it's 2. I will explain it in a minute. So, and what makes it special, what means group, I will tell you in a next minutes. What makes it special, that the determinant equal to 1, sometimes equal to the -1. If we have not a right orientated by the left orientated frame, for example, if it has something to do with the mirror. Yes. And the inverse equal to the transpose. And it's much more convenient to compute the inverse computation-wise than the inverse. So R12 equal to the R21 transpose. So if I'll write, for example, for the P2, the proper notation will, for the rotation matrix P1, will look like this: x1, comma x2, x1, y2, y1, x2, x1, x2, like this. What the fuck is this, right? I mean, this is something which is called inner product. So the inner product, it's also called the dot product. Why it's called the inner product? That you have a vector and you do operation with another vector, and the result belongs to the vector space. So it's like an operation inside a vector space. And the inner product is denoted like this. And it equal to the linear combination. So it's like a vector v1, v2, v3, and a column v1, omega 1, omega 2, omega 3, and it equals to the v1 omega 1 plus v2 omega 2 v3 omega 3. And it's also will be equal to some scalar. So it's called inner product. Inner product. Sometimes it's called dot product. Product. Sometimes it's also called scalar product, but here you need to be careful that sometimes also if you have a vector and you multiply it with a scalar, it's also called a scalar product, that you multiply a vector on a scalar. But sometimes they called scalar product when you multiply a vector with a vector and you get a result, the scalar. So here you have a vector and another vector, and the result of the multiplication is a scalar. Okay. So the full derivation why this matrix looked like this, you can find in the slides or in the Stefano book that I mentioned in the Telegram. I think it will just waste time. So the intuition is almost the same, but there you can find the proper mathematical derivation. And the inner product has extra structure that allows us to measure the angle between vectors. So basically we can say something about angles because we have operation of the inner product. And the inner product is like an extra structure. If you talk about a vector space, in general, vector space has only two operations. So like vector space, you have just like a vector, and the vector is like an arrow, it's like a bunch of numbers, so the vector. And for the vector space, you have just two operations. You can multiply it on a scalar, so the scalar means that you scale the vector, and you can sum vectors. This will be the But since we do work not just in the vector space, but in Euclidean space, it is a vector space that has the property of inner product. So the Euclidean space, like the 3D space, it's like a vector space plus it has this inner product. And since it has its inner product that we just established, this thing has a structure that allows us to tell about norm, the length. It allows us to tell about angles between vectors. And the cosinus between vectors will be just this inner product divided on the norm. So basically from here we can say that the inner product of two vectors will be norm of 1, norm of 2 times cosinus. So, and if we put it here, we know that the length of x1 equal to 1, x2 equal to 1, since it's unit vectors. And what will be the cosinus between x1 and x2? Theta. So, and if you put this formula here, you will get the same result as we have done previously. But here you can see that you have a columns expressed in the first frame and the lines expressed in the frame of this two. And you can easily write it down, write something similar, but for the 3D space. It's like x1, x1, x2, y2, z2, y1, 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 z1, 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 x2, 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 x1, y1, z1, and this will be the same stuff. y2, y2, z2, z2. And for example, for the system that we just derived, what will be the value for the x1 times z2? 0. And what will be z1, z2? 1. Since the rotation along the z-axis. This stuff will be rotation matrix for the 3D space, yes, with the 3 dimension, and it will be SO3. 3 stands for the dimension of the space. So, and it's a spatial, but also it's a group. Group it's a mathematical group structure. It means that you have a set of something and operation. For example, if you have like how it's called natural numbers, and for example a plus. In order to be a group, you need to have a property which is called closure. And it means that you have an element, you do operation with another element, and it belongs to the set. For the natural number, it holds. For example, 1 plus 2 equal to 3. Okay. The second, which is called associativity. It's like one operation with another element C equal to the this stuff. For the sum, it also holds for the natural numbers. And you also have something which is called identity. That you have some element such that if you do operation with another element, you will have the same element. It's like plus 0. Is it natural number 0? I'm not sure. I think yes. 0. I mean, is it?
If it's not, then we can't say it's a group because it doesn't have an identity. If it's not a whole number, natural group, then we can't say it's a group with the plus
because. If 0 belongs to natural numbers, then it holds. If it's not holds. I'm just not. I do not remember. Is it belong to the natural number or not?
No, I think there's like series on both sides.
Natural number start from 1. 0 is a whole number.
I didn't get it.
0 is a whole number, not natural. Natural number starts from 1. 1, 2, 3, 4.
1, 2, 3, 4. So it doesn't belong. It doesn't.
No.
No. So okay, it already doesn't hold. But if we go to it is. Wikipedia says it is. Probably we need to another resource of information. But still, if we go further, it also has to have the property.
So it's debatable even It's debatable in Wikipedia. Some say it is, some say it's not.
Debate. All right.
Yeah, debatable. Yeah.
Okay. So, but if we go to the final property, it need to have something like this, that you have some kind of operation, such kind of element, such that the result will be this identity. And for the natural numbers, it's not the case, because you do not have -1, -2. So if you have like Zahlen, like Z, it's called from German Zahlen, it has negative numbers. So it will, and with the operation of plus, of summation, it will be the group. But with the multiplication, it won't be. So this is the idea of the group. And the rotation matrix, it is a group. So you can multiply one matrix with another matrix and with another matrix, and you will get a matrix that represents a coordinate transformation from 4 to 1. It's like if you would like to go from coordinate representation in frame 4 to some kind of 1, you can do this chain rule, just matrix multiplication. So associativity holds, but it doesn't commute. I mean, 1 over 2, 2, 3, and the 2 are, and this stuff, they will give you different results. It is not the same. And if you take R and if you multiply it with the inverse, it will be the same as the transpose, and it will equal to identity, right? Great. So here you can see the proper description of these properties, and what makes it special, that the inverse equal to the transpose and the determinant equal to 1. Whew. Nice. Let's assume that we have a body. And a point like P. And we have a frame which is fixed with this body rigidly, and it will be the frame Psi. So it will be the Xi, it will be the Yi and Zi. And let's think that it rotates around another frame J. We know that we can write that Pj, okay, Pj equal to Rj I Pi. Do you agree? Let's take a time derivative. So the time derivative will be R dot J I Pi plus Rg I Pi J. Do you agree? What can you tell about this guy?
It's Vg.
Hmm?
It's the velocity of V.
Look, Pi, it is this distance, which is fixed. What will be the time derivative of a fixed value? 0. So the Pij equal to the R dot Ji Pi. And for the Pi, we can write that it equals also Rij Pj. And we can put it here. And it will be Rij I Rj I J, P, J. So the time derivative of a position equal this time position times something which is equal to this stuff. And actually this is the angular velocity. And look, the angular velocity, it's not r dot. It's r dot times r inverse. So it basically you can see on the letters, so it's r inverse. And if we'll write for the pi, so we can do the same for the pi. It will be r I j p j I p I. No, it will be different. So since I'm not sure that it is correctly, I will delete it. The proper value you will see in the lecture notes. But the idea, if you express it in another frame, you switch the position. So since I'm not sure, I will just delete it. So this, what will be the dimensity of this matrix? 3 by 3. A lot for the angular velocity, right?
Yeah, but it's symmetric.
Yes, it's something which is called skew symmetric, and it is denoted with this tilde, and we will write here that this is the motion of a body. What is the frame of the body? I or J? Which one is fixed? I. So the body I moves in respect to the J, and this stuff is expressed in J. So it has 3 scripts. So about the notation, let's assume that you have angular velocity A, C, B. It means that it is angular velocity of psi A. Let me change colors here. In respect with psi B and expressed in psi C. It's like we can describe how this fan rotates around, I don't know, table, and we can express it in some kind of third frame. And this is the notation that you will see at Stefana's lectures. It's his materials. Ken Lynch used only 2 letters, so it doesn't allow to do this C. So this kind of more universal structure. So and it also has kind of mnemonic rule that we need to write to choose this this term and put it on the main diagonal. Then another element, put it here, and the same configuration of letters that J on the top, I on the bottom, and this means that we need to put a dot here on the left. So if it's like a mnemonic rule. So if we do I, so the same motion of I in respect to J, but expressed in I, like not in the space frame, but in local frame. So we put I here, J here, and where should I put a dot? On the right, yes, because of this configuration. Yeah, so it is this stuff that I was drawing right here, that if you change position, so it does not commute, that if you change position, you will get different result, and basically you will express the same motion in a local frame instead of space frame, or opposite. Great. So if you do, for example, something which is fixed to the space, like a manipulator, which is fixed to the ground, you need to express it in this fixed frame. But if you have a mobile robot, you can express it in the local frame of the fixed body of the floating base, for example. So, and it's something, we already told us that angular velocity is a 3x3 matrix, and it's something which is called skew symmetric. So, for example, if we have a vector x, which is x1, x2, x3, the skew symmetric representation of it will be 0. By the way, it has a special property that the transpose of itself equal to itself with a minus, and it's called symmetric. What will be the elements on a diagonal? Zeros. x3 minus x3, minus x2, x2, x1 minus x1. So basically, this stuff is this kind of representation of angular velocity. So you have also omega x, omega y, omega z, but omega x will be here, omega y will be here, omega z will be here. And skew symmetric representation is also used for the vector product. It's something which is called skew symmetric matrix. And this skew symmetric matrix is used for the vector product. So for example, if you would like to if you have a vector x and you would like to have a vector product, sometimes it's denoted as a cross product. So the result will be skew symmetric representation of x times this vector. Vector product. It's kind of like a cross. Sometimes it is denoted with this hat, sometimes with the x. Great. And you can really think that why we need to compute vector product. It's like you have a vector, this x, you have a vector y, and the result of this will be the third vector x, which is perpendicular to them. Yeah, and it's like analogy for the 2D mechanics, for the simple mechanics, we know that angular velocity is something which is applied here, like in 3D space. It's like this is the vector of angular velocity. And this is the linear velocity, and it's like a radius vector. So in order to compute omega, you take radius vector, you multiply it with the v. Actually, different, the opposite. So you take radius vector, you multiply it with the v, and the result is angular velocity. So the angular velocity, linear velocity equal to omega r. And actually it is a vector product.
We also needed to compute the derivative of the unity vectors.
Okay, yeah. So far we just considered rotation. But in general motion, you can say that you have some kind of frame 1, P, J, you have another frame, Pi, and you have some kind of physical point P. And you also has change not only on orientation, but displacement. And in this case, we use the following notation that Pj equal to rotation matrix, we already know that, Pi plus bias. And also there is a derivation, but finally the way how we write it down will be the following. We use something which is called homogeneous transformation matrix. And it will be like Pj equal to the mass rotation matrix, Pji, vector P, the small one, not the capital, and the capital P. And the P for example, J, it is like X, Y, Z, and 0, I believe. And not 0, 1. Since this matrix is 4 by 4. And it's something which is called homogeneous transformation matrix that describes completely position and orientation of 3D body in a Euclidean space. And it's also something which is called a spatial but Euclidean group. It's called spatial Euclidean group, or SE3. 3 for the 3D motion in 2D plane it will be SE2. So Pj equal to the IHJI Pi. The inverse of H doesn't equal to H transpose. It doesn't have this beautiful property as for the rotation matrix. It is different. It is not complex, but it is different, and you can compute. But actually, so it's a group. So all these properties the same. How inverse looks like. This O means position vector P, x, y, z. You also can use a chain rule. And we basically we can do the same trick here. Let's try to do this. So P time transpose J equal to the P Ji Pi plus H Ji Pi, the capital P. And for the same reason, it will be 0. But it only holds for the rigid body. For the elastic body, it's not the case. Right? And Pi equal to the Hij Pj that we can put here. So basically, Pj equal to the Hji Hij Pj. So, and you also has something strange. What will be the dimensionality of this matrix? 4 by 4. And who is it?
It's the skew symmetric of the homogeneous representation of the angular velocity.
It's not only angular velocity. It's a full velocity. It's a spatial velocity. And it's something which is called twist. It's flow, bone graph speaking. It is like a spatial velocity. And it is denoted with the letter T. So this T so I was it was rotation of I in respect of J expressed in J with a tilde equal to the H, the same mnemonic rule. So if we want to have the same motion but expressed in J coordinate, so what should I write here? Right here, what should I write? Here, what letter, I or J? Basically, it is the same. So I, right? Diagonal. And then the second term, and I need to take a look at this configuration, so the dot will be here. This twist equal to the, so it's 4 by 4 matrix, and angular velocity in a skew-symmetric form, velocity in a like a normal form, and a 0 here. So it's like this is the angle position, then 0, 0, 0. So this is the angle, then V is in 0. So angular velocity here, V is here. Okay? We have like 7 minutes, and I would like to make an one point. So let's assume that we have 2 bodies, and each of them has two frames, different frames. And it is called P1, it is called P2, it is P3, P4. So we know the mnemonic rule, and let's assume that we would like to write down what will be the velocity of the frame 3 in respect of frame 1. It's like how the blue body rotates around or moves around the yellow one. It's like the CR rotates around, moves around in respect of 1, and let us write it, express it in a 1 frame. So the mnemonic rule 1, 1, 3, 3. Where should I put a dot? On the left, on the right, left. Okay. Let us assume I would like to do the following, but the same, but for the not 3, but for another frame that belongs to the same blue body. So it will be 1, 1, 4, 4. Where should I put a dot? Left. And we know that H is a group, and it has a property of associativity, so the chain rule. And we can say that H1 3 equal to the and times 3 4 equal to the H1 4. It's like this, and then this should be deleted. So, and we can write like H1 3 3 4 like derivative for 1, H1 3 H3 4 plus H1 3 H dot 3 1. Do you agree? What can I say about this stuff? What can you say about it? It's 0, since 3 and 4 belongs to the same body, and the time derivative is 0. H1 3 H3 1 H for 1, so h13, h31. It is the same. And you can see that the twist for the frame 3 and for the frame 4, they are the same. So the velocity are the same. It's just like angular velocity, the ordinary angular velocity is the same for all the points. But twist is not only angular velocity, it's just the whole velocity with the translation as well. But it's the same for all the bodies, all the points on the body. And we can play it as we want it. So we can play with another frame. So we can express the same motion in different frame, and we'll find it out that also the twists are the same. So the twist is constant for a body, and it doesn't depend on the frame, on your choice of frame. So for the body, the twist will be the same.
But here we didn't change the frame that we represent the twist in.
Sure.
You said that the twist is not affected by the frame that it's represented in, right?
Mm-hmm.
Yeah, but here we didn't change the representation frame. It's in the both of them it was one.
I mean, you can do this for any frame. You can change the numbers, but still it will be the same. You can play with it. And the point that I wanted to make, so here we know that this stuff is Pj, so P dot j will equal to the twist times Pj. So the twist is something else. So the twist is a spatial velocity. It represents the full velocity. It's not only angular velocity, but the translation. But it's kind of strange translation velocity, since it's constant for the whole body. And if we would like to have the velocity that you're familiar with, you need to know what kind of point do you would like to study. So you need the position, and this p dot is something that you know. So this will be something in a meter divided by second, for example, or kilometer per hour, meter per second. This twist is something which is strange, and this is the meters. So this v will be a different one v. This is a strange v. It's not. This v is not meters per second. So sometimes you will see that v just a vector that compose angular velocity with a v, and that this is radian per second. This is m, and they will say that it twist. It is not. It is not twist. It's just a vector with all the angular velocity and linear velocity. In order, this stuff is a p dot, because this classical velocity is different for the points. It's different for the coordinates frames. You know that, for example, one pendulum, the velocity of the frame is the linear one, like meter per second, is 0, but for this end it's not 0. But the twist will be the same. because twist is something which is called a screw. It's like a screw, and there is a theory which is called screw theory, but we'll cover this in the next lecture because I have a video call in 7 minutes, so I need to finish the call, and the second part of today's lecture will be with Igor. Yes. Thank you. Now I need to go.